Homework last night was worksheet number 4. It was on power. The answers to that worksheet are up on the board right now. Have a look. See if you had any trouble with any of them, if you made a mistake in any of them. And if you did, then raise your hand and we'll go over that question. Yep. 7. 6, I'm thinking probably we'll have to go over 2. Is that right? No? Yes? Okay. Yeah, I was pretty sure by just the level of difficulty of number 6 that we'd have to go over it. Any others besides 5, 6 and 7? No? All good? All right. 6 and 7 it is. Number 6 said, I thought this was a hard question. Okay. Number 6 says a bicycle is pedaled at a speed of 22 kilometers per hour. We know that we don't want to use kilometers per hour, right? We want meters per second. So we're ultimately going to convert that to meters per second. For 20 minutes, we know we're going to convert that to seconds as well. The power output of the cyclist is 400 watts. What's the average force that the cyclist applied on the bicycle? Let's write down some givens here, okay? We know that V is 22.0 kilometers per hour. When we convert that to meters per second, it's going to be 6.1111 meters per second. 22 times 1,000 divided by 3,600 gives us 6.1111 meters per second. Now my time is 20 minutes, which corresponds to 20 times 60. To convert it to seconds, is going to give me 600 or 6,000? 600 seconds. That's right, isn't it? 600 seconds? No, it's not. 1,200 seconds. What am I talking about? 1,200 seconds. Thank you. What else we get here? The power. The power here is 400 watts. And we want to find the average net force, the average force that's applied on it. All right. What I'm probably going to do here first is write down the power equation. Okay, we know that involves force. We know that it involves power. Just because we write down the power equation doesn't mean that that's going to be what we're going to end up using to solve this question, but it's certainly valid. Okay, if the problem involves power, we're allowed to try this. We don't know what to try? Okay, try something that you know is valid. Power is one of those things. Now, here's what I did. I think this is kind of tricky. Some of you guys did it this way. Some of you guys did it slightly differently. Okay, I'm going to do it my way first, and then maybe we can take a look at the other way. I said work is also equal to F times D. So instead of solving for work, I actually plugged the expression for work in there. Instead of P is equal to W over T, get work, then plug it in there, I just subbed in the equation for work into there. Okay, and what the benefit of that to me was that D over T, we know what that is, right? D over T is equal to V. V is equal to D over T. So my equation became F times V. I replaced D over T with V. Now I know the value of F. No, I'm solving for F, I guess. So I rearrange this. I get F is equal to power over velocity. The power here is 400 watts. The velocity here is 6.1111 meters per second. And when I solve for that force, I get 65.5 newtons. Now, how many people did it that way? They subbed in delta D over delta T and then replaced that with V. Okay, a handful of people. Hey, those of you who got the answer but did it slightly different didn't actually do it that much different. It may look like you did, but it's not really that much different. Can anybody explain to me what you did if you got the right answer but didn't do it quite this way? Yep. Found the displacement. How'd you do that? Okay, good. So V is equal to delta D over delta T. Rearrange that. We get the displacement. It's V times T. That's 6.1111 times the time of 1,200 seconds. And what'd you get for that? Because I don't have that calculated on my answer sheet. 7,332 meters. All right, now that we have displacement, now we can go back and say work is equal to F times D, right? No, we can't actually yet because we don't know what work is. Now we can say power is equal to work over time. That's what you did, right? Work is equal to power times time. 400 watts times 1,200 seconds gives me 480,000 joules. Now that we have the work, now we can turn around and say W is equal to F times D, and solve for F. The work is 480,000 divided by 7,332, and I think we should get the same number there, right? 65.5 newtons. So it looks quite a bit different than the method that I used, right? But in the end, you really did the same thing. You just did it separately, right? You just did it in stages separately. Look, what did I do? I used P is equal to W over T. I used W is equal to F times D. I used V is equal to D over T. I used three equations, right? I just put them all together. You used the exact same three equations. You just did them separately, that's all. There's no, I wouldn't suggest that one is better than the other. I like the first way, but I'm biased because that's the way that I did it. I don't think it's any better than the second way. How many people got the right answer there? Good. That's a tough question. So if you got that answer, that's very good. Whichever way you got it. Okay, number 7 now. 7 says a small engine produces 6,000 joules of energy per second. How far would push a 3-kilogram object if it's able to apply an average force of 200 newtons on the object? What it really should say is, how far will it push the object in 1 second? How far is it going to push it in that 1 second, right? It produces this much joules per second. How far is it going to push it in that 1 second? That's the way it was meant to be. Now, if you interpreted it that way, you had a couple ways of answering this question. You could say work is equal to F times D. You're looking for D, so you could say D is equal to W over F. The work here is going to be 6,000 joules divided by the force of 200 newtons. It's 30 meters. Done. We had 6,000 joules per second. What's the distance in 1 second? Well, this is how many joules we had. This is how many newtons we had. This is our distance. Now, if you did it as a power problem, which probably a lot of you did, we got power is equal to W over T. Okay, that allows us to solve for power. Right? Power is equal to work, which is 6,000. The power is 6,000 joules per second, 6,000 watts, times a time of 1 second. It still gives us 6,000 joules. Okay, now we want to find the displacement. We'll do the same thing as we did the last method here. F is equal to W over D. 6,000 divided by 200. Gives me 30. How many people got 30 for that? Good. Okay, that was a good question, except that it wasn't worded all that well. Okay, it should have been more clear that we were dealing with a time of 1 second there, and it was in there, but it wasn't all that clear that we were dealing with that time of 1 second. Okay, if you got it, good, excellent. Any questions on those two questions, or any further questions on any of the rest of them? No? All right. So what have we done so far with our whole energy unit? Our energy unit, which is very, very short, right? Because in the end, it's really a part of dynamics. I told you guys that before we had our dynamics test. We had a choice of combining this on our dynamics test or having a separate kind of mini test. It's a short unit. What have we done? Kinetic energy. Potential energy. And within potential energy, we talked about gravitational potential energy, and we've talked about elastic potential energy or spring potential energy. We also talked about work. And the work energy theorem. That's W is equal to delta E. We talked about power. And then finally today, we're going to talk about the last thing in energy, the last part of our unit, which is going to take us a couple of days, but to prepare us for our test early next week, conservation of energy. Conservation of energy. An object moving has kinetic energy. An object at a height has potential energy. An object that's on the end of an elastic that's stretched has elastic potential energy. An object that experiences friction or is pushed experiences a change in energy. In other words, a work. Okay, we can find the power experienced by that object or produced by that object by dividing that work by time. But all in all, it comes down to this. If we take into account all of the energy in the system, not the energy of Braden, not the energy of John, not the energy of Tara, but all of the energy in the system combined of all three of them, all the potential, all the kinetic of all the things, then the total amount of energy will always remain the same. That's the law of conservation of energy. The total amount of energy never changes. Okay? Braden starts moving, he gains energy. Okay? Something else loses energy. Okay? If he gains kinetic energy, he loses potential energy. Okay? As you drop a rock from the top of a cliff, the rock gains kinetic energy, but it loses potential energy. Okay? In other words, the total amount of energy remains the same. Two cars hit each other. One car gains energy, one car must lose energy. The total amount of energy remains the same. Slam on your brakes. The other day it was Friday. I was driving through Johnston Canyon out between Banff and Lake Louise. It's that kind of that back road towards Lake Louise, if any of you guys know it. There's some deer on the side of the road. I slow down because I see these deer and I'm thinking, I hit a deer once. The day I got my learner's permit, by the way, I was 16. I got my learner's permit, hit a deer that day. It was almost the exact same situation, except I was more prepared for it this time. I slow down. I'm ready to stop on a dime. The deer runs out just like he did that day that I hit him 26 years ago. Except this time he doesn't run right at me. He runs across the road. I lay on the horn because there's another car coming the other way. The other car slams on the brake. The deer literally jumps right over top of his roof and drags his legs, drags his feet on the roof of this car. The car slammed on the brakes and it skidded and it made some black marks on the pavement. The car had kinetic energy. Now it has none. Total amount of energy was lost, right? No, because what happened when he slammed on the brakes? What happened when he made black marks on the pavement? It was friction. Friction's a force, not an energy. But that friction transforms the kinetic energy into... I didn't get out of the car and touch this guy's wheels, but I'm pretty sure those guys' tires would have been pretty hot, right? Because the kinetic energy was transformed into thermal energy. The total amount of energy remained the same. It's just that it was transformed from one type to the other. That's what we're going to talk about today, this law of conservation of energy. The total amount of energy is going to remain the same. Energy can't be created. It can't be destroyed, but it can be transformed from one type to another. It can be transformed from kinetic to potential, from kinetic to thermal, even some sound. Listen, I heard when the guy slammed on his brakes, like it made a loud noise. This guy's squealing on the pavement here. Some of the kinetic energy was transformed into sound, most of it to heat, but some of it into sound. But none of it was created, and none of it was destroyed. Kevin just asked a good question. He says, what happens if you drop a rock from the top of a cliff? Okay, he walked through this with me. He told me what happens here. He says potential energy that it has at the top of the cliff is converted to kinetic energy. So you're not losing any energy there, right? It's a conversion from potential to kinetic. You have less and less potential as it falls, and you have more and more kinetic as it falls, right? So energy is conserved. The total amount of energy remains the same. But then it hits the ground. He said, and then it doesn't have any kinetic energy or potential energy. So energy is lost then, right? Energy is destroyed then, right? Energy can't be destroyed, can't be created or destroyed. So what happens? Where does the energy go when the rock hits the ground? Yeah? It's transferred to the ground. What it does, Kevin, you don't feel this unless it's a really, really big rock, but what it does is moves the earth. When you drop a rock on the earth shakes. It's an earthquake. Hey, the earth shakes. That's kinetic energy in the earth. Now, why don't you feel it? Most of the time, why don't you feel it? Yeah, yeah, it's such a small amount of energy in the grand scheme of things that you're not going to feel the movement of the Earth as a result of that, right? Let's say the rock has 30 joules of kinetic energy just before it hits the ground. Okay, this tiny little rock that just fell from the cliff, that's going to have a noticeable movement with 30 joules of kinetic energy. But if you transfer that 30 joules of kinetic energy to the Earth's going to move. But how fast is it going to be moving with 30 joules of kinetic energy? Almost zero, right? Because of its mass. That makes sense? There will be a little sound energy produced as well. You're going to hear it hit, right? So some of the energy will be lost. Not all of that 30 joules will be transferred to the Earth. Some of it's going to be dissipated to sound, but it's still not destroyed. Some of the energy may even be transferred to heat. As it hits the ground, it warms it up a little bit. Not very much, but it warms it up a little bit. So maybe now you lose another joule or two. But again, it's not destroyed. It's just transformed into another kind, heat. But most of the energy would be transferred to the Earth because the Earth can move, just not very much because the Earth is so heavy, right? Good question. Now, we do know that sometimes energy is added to a system. We do know that sometimes energy is lost. Energy is taken away from a system. If we're looking at Kevin's example here of the rock falling, and we define our system as just the rock, then energy was taken away from that system, right? If it wasn't destroyed, it went to something else outside that system. Sometimes it appears as if energy is added. Energy is created. You got a sailboat out in the water. It's just sitting there. It's not moving. A wind comes up. The sailboat starts moving. Kinetic energy was created, right? No, kinetic energy was added to the system, but it wasn't created. It came from the wind, from the kinetic energy within the wind. So sometimes you add energy to a system and take energy away from a system. There's a change in energy, even within the whole system, but it's still never created or destroyed. Now, what are we going to use this for? And this is a pretty important concept. This is arguably the most important concept in all of physics, the idea of energy conservation, the idea that we can't create or destroy energy. It goes from physics 20, halfway through physics 20, where we are right now, and the type of problems that we're going to solve with this, all the way through the creation of X-rays and why things get heavier as you speed them up, approach the speed of light, and why time slows down, and all kinds of crazy things like that. Where are we going to use this in physics 20? Well, we're going to use it in mechanics. When we have, say, a roller coaster at the top of a hill, goes down the hill, the kinetic energy is converted to potential energy. We're going to use it when we throw a ball into the air. Kinetic energy is converted to potential energy as it rises up into the air. We're going to use it when we have a swing set going back and forth like this. The little kid on the end of the swing set is converting or has his kinetic energy converted to potential energy as he goes up and potential converted to kinetic as he goes up. Okay, we're going to limit our use of conservation of energy to mechanical energy problems. And when we do that, we're always going to start off the problem by saying this: EI equals EF. In other words, if we're accounting for all the energy, okay, all the energy, including, Kevin, the energy of the ground, the kinetic energy of the ground as it was hit by the rock, including the thermal energy experienced, or the thermal energy of the road and the tire as the car slams on his brakes, if we account for all of the energy, then the total initial energy will always be equal to the final energy, EI equals EF. And that's the way we're going to start off all of these problems, okay, all of these problems. Write down EI equals EF. Now, what are we going to do with that? How are we going to turn that into an actual legitimate way to solve a problem? We're going to identify what kind of energy you have in the initial, at the beginning, and what kind of energy you have at the end. There's only three kinds you can have, at least in physics 20, there's only three kinds you can have: kinetic, gravitational potential energy, and elastic or spring potential energy. Ask yourself three questions. Okay, at the beginning of your problem, do I have kinetic energy? Well, if it's moving, you've got kinetic energy. If it's not, you don't. Do I have gravitational potential energy? Well, if it's got a height, you've got gravitational potential energy. If it doesn't, then you don't. Do I have elastic potential energy? Well, if you've got an elastic that's stretched, then you get elastic potential. If you don't, then there isn't. Ask yourself those three questions at the beginning of the problem and at the end of the problem. And then sub in the equations for each of those types of energy. All right? Let's do a problem that's not in your book. I'm just going to draw it out here. I'm going to ask you to copy this out and then solve it with me here. We've got a roller coaster car that's at a height of 50 meters. It's at rest at the top of the hill. You know what? Actually, let's not make it a rest. Let's give it a little bit of a speed, but a small speed. We've got another hill over here on the right-hand side that's a height of 20 meters. I want to know how fast the roller coaster car is moving when it reaches the bottom of the first hill. This is a question that's very much like one of the questions you're going to experience on your field trip assignment when we go to West Edmonton Mall. What's the speed of the car at the bottom of the hill? By the way, the height of the first hill on the roller coaster at West Ed is 50 meters. You're going to climb your way up to the top of 50 meters, and then you're going to, in a matter of 3 seconds, plunge almost straight down 50 meters towards the ground. How fast are you going to be moving in that 3 seconds? Well, we know that the total energy of this roller coaster cart is going to remain the same. It's not going to change. That would violate the law of conservation of energy if it changed. It's got to stay the same. But it's going to be converted from one type to another. It's got a little bit of kinetic at the top and a lot of potential. What's it got at the bottom? A lot of kinetic and no potential. Let's say EI equals EF. Now let's ask ourselves those three questions. Is there kinetic energy at the top of this hill? Yes or no? How do you know? It's moving, right? There's kinetic energy because it's moving. So let's put in an equation for kinetic energy, 1/2 mvi squared. Is there gravitational potential energy at the top of this hill? Yes or no? Kevin? Yes? How do you know? Good, because it's above the ground. It's got a height. Relative to the ground, it's got gravitational potential energy. Now, relative to the top of the hill, it doesn't, but presumably we're going to define everything relative to the ground here. So there is gravitational potential energy. Let's add those two together. The initial kinetic energy plus the initial potential energy. Is there any elastic potential energy here? Is there any elastic involved here? No, so there's no elastic potential energy, right? That's it. That's all we have. Kinetic energy plus gravitational potential energy equals, what kind of energy do we have at the bottom of the hill? Do we have kinetic at the bottom? Is it moving? Who said yes? Yes, it is. It's moving, so it's got kinetic energy. We're going to say that's equal to 1/2 mvf squared. Is there gravitational potential at the bottom of the hill? Is there a height? There's no height. Listen, ask yourself this. Can it fall any further? We're at the bottom of the hill. Can you go any further down? No, so there's no gravitational potential there. Is there an elastic? No elastic potential either, right? We started off with kinetic and potential. We end up with just kinetic, but the total of the energies on both sides is going to be the same. Let's plug in some numbers here and solve for VF, the final speed. Hey, one thing that I notice here mathematically, save yourself a tiny little bit of work. Anybody see it? Why? Yeah, if one variable appears in every term on both sides, you can cancel it out. Doesn't matter what the mass is. All right, so let's plug our numbers in here. My suggestion would be to not rearrange this until after you put numbers in. VI was, I think it was 2, wasn't it? Yeah, 2 meters per second. Who was it yesterday that was asking me about negative, positive? Kate, was it you? Yeah? What do we make this, positive or negative? 9.81. Yeah, because we're talking about energy, right? Make it positive 9.81. HI was 50 meters. Okay, let's get the numbers on the left-hand side. A half of 2 squared is 2. 9.81 times 50 is 490.5. 2 plus 490.5 is 492.5. How do you get rid of the half? There's 2 ways here. One is divide by half. The other way is multiply by 2. Either way, we're going to end up with, what is that going to be? 900. It's 490.5 divided by 2. 985, I think. Now let's square root that. Square root of 985, what is that going to be? 30, about 31, I'm thinking. Is it 31? How many digits should we be here? 2 digits? 31 meters per second. Where'd that speed come from? It came from potential energy. We didn't produce any energy. We didn't destroy any energy. We just converted a whole lot of potential energy into a whole lot of kinetic energy. So it went from a speed of 2 meters per second to a speed of 31 meters per second. 31 meters per second, by the way, is somewhere in the range of 110 kilometers per hour. So in a month's time, you guys are, how many people have ridden the Mindbender at West End? Only a handful. Wow. In a month's time, when you plunge that 50 meters in a time of 3 seconds, you're going to go from 0 to 110 kilometers per hour in about 3 seconds. If that scares you, good. That's my favorite part of this trip, is watching your faces as you're terrified as you go on this ride. Does that make sense? Is this okay, guys? Let's try another example that's going to look a little bit different, but boils down to the exact same thing. One more quick problem, guys. We're going to say this time I'm going to throw a rock or a ball up into the air. Okay, it starts with a speed of 10 meters per second. The question is, how high is it going to go? What's the maximum height of the ball? Now, we could solve this problem with one of our kinematics equations that we learned early on in the year. We could have done this problem in September, sorry, not in September, but in February. We could have easily done this problem in February. But now we can use the law of conservation of energy to solve it as well. We have another method here. EI is equal to EF. What kind of energy does the ball have on the ground when it's thrown upwards? What is it? No. After it's released, okay? Now, as it's in your hand and I'm ready to throw it, yeah, there's potential energy. It's chemical potential energy inside my body, right? But after it's released, just after it's released, what's it got? Nope. Just after it's released, it's still on the ground. What has it got? Kinetic. It's moving, right? It doesn't have potential energy when it's on the ground, right? Look, it's on the ground. We don't say it has potential because it's going somewhere. We say it has potential because it's got a height. There's no height here. It's on the ground. There's just kinetic energy because it's moving. Now, when it reaches the top, what happens to it? Slows down, slows down, slows down, and stops. What kind of energy does it have at its peak height? Potential, because it's got a height. Does it have when it reaches the top, it stops. There's no kinetic, but it does have potential. We can cross off the m's, just like we could in the last one, because it's in every term. The initial speed is 10 meters per second. G is 9.81, positive, because we're talking about energy here. Solving for the final height here. 10 squared is 100 times half is 50. HF is 50 divided by 9.81. So that's going to be somewhere in the range of 5-ish, okay, 5.1 meters. So a problem that looks completely different. Find the max height of the ball versus find the speed of the car when it reaches the ground. Problem that looks completely different. Ends up being solved in almost the same way, right? EI equals EF. Ask yourself the same three questions. Do we have kinetic energy? Do we have gravitational potential energy? Do we have elastic potential energy? Sub in an equation for each of the types that you have. Solve. Okay, here's what I'd like you to do for homework, please. You thought you were getting out of this. You weren't. I'd like you to do questions 1 to 5 on worksheet number 5. There's 6 questions on that page. Please do 1 to 5. We'll have a peek at those tomorrow.